growing and changing all the time. And the next thing we really want to do is involve a lot more of the people who come to these lectures and support us in various ways. So a museum association is being formed to help advise us on the seminars. And one of the first events that's being planned is a museum excursion to see the son of Whirlwind, the SAGE computer, which is at North Bay, Canada, a vacuum tube machine that is still serving our defense system. And we will plan that for some time in the fall. Anyway, there are a variety of things to be planned and to be done, and our first organizational meeting will be March 23rd at 4 in one of these buildings. And anybody, if you sort of leave, you can log your name in to the terminal at the reception and say you want to know more about the association, or hand us a slip of paper, do anything you'd like, and love to have people come. I also want to say that have a wonderful volunteer chairman to start it all, and that's Kitty Selfridge, who's here. So you can also say something to Kitty. And with that, the other thing is, if you haven't gone up and seen the Pioneer timeline of the first 12 computers, it's on the balcony. And like all things, we had hoped by now that you could walk from the balcony right over to MR2, but the wonderful covered walkway to the other part of the museum will probably be done just in time for the good weather. So you'll have to put on your coats to go to the reception. And now I would like to introduce Maurice Wilkes, who really doesn't need introduction because he started this whole series and was the first one to talk, who will say something about Dr. Burks.
Thank you, Gwen. A week or two ago, we had a lecture from Dr. Brainerd from the Moore School of Electrical Engineering in Philadelphia, who told us his view of the beginnings of the ENIAC. Now, he was a senior faculty member of at that time, and was in charge of the project, and as he explained, what that meant very simply was that if it had been a failure, he would have been expected to resign. Tonight, we have a view from the other end of the spectrum. Dr. Burks took his PhD as late as 1941 and went to the Moore School to take a course in electrical engineering with a view to war service. And that war service turned out to be working on the ENIAC. So tonight we are going to hear about the ENIAC project from the position of a young man who just qualified. He worked on the ENIAC project and made considerable contributions on the engineering side, although his original training was that of a philosopher. And after the war, he went back to Michigan, and I regret to say relapsed to some extent from engineering and became a philosopher again, but not entirely. He was one of the founders of the computer science department at Michigan. You know, that wonderful subject which no one quite knows what it is, but it's very wonderful, and is at this moment professor of philosophy and computer science, a joint appointment, and he publishes in both areas. May I introduce Dr. Burks.
Thank you very much for that kind introduction, Professor Wilkes. Ladies and gentlemen, my talk is on the origin of the stored program. The The stored program computer differed from its predecessors in two fundamental respects. Hardware: it contained a new kind of read-write memory of much greater capacity than any previous memory, large enough to store the program as well as the data. Software: it executed a new kind of program language, one that took advantage of the new way of storing programs. This most important historical achievement did not come about in a straightforward way, but in a convoluted, indirect manner. For this reason, the origin of the stored program computer is best understood against the backdrop of a fictional account of its development from earlier general-purpose computers. I will compose a story of how the modern computer might have developed in four natural technological stages, starting from Charles Babbage. Each of these stages actually occurred, at least in part, but most of the temporal and causal connections of my fictional story did not. The first stage of the derivation is Babbage's analytical engine. This mechanical general-purpose computer had a simple, modern, centralized architecture. A central arithmetic processor, he called it the mill, and a read-write store for numerical data consisting of many mechanical registers. The program was punched on a chain of Jacquard cards. The second natural stage of my story is an electromechanical or relay version of Babbage's general-purpose computer. A relay general processor and enough relay registers to store the numbers to be operated on. The program is now on punched paper tape and is sensed electrically rather than mechanically. In both the first and second stages, the numbers to be processed are stored differently than the program directing the computation. The numbers in mechanical or electromechanical registers, the program in read-only punch cards or tape. This is wise design. Punch cards and tapes can pretty well keep up with mechanical and electromechanical registers and switching mechanisms and are very much cheaper. The third natural stage in our hypothetical account is an electronic version of the central arithmetic processor and read-write data store of these first two stages. Fast electronic circuits for processing numbers and equally fast electronic registers for storing them. But programming now presents a problem. Electronics is orders of magnitude faster than the earlier technologies. Even at the beginning, it was 1,000 times faster. A program on punched media could not possibly keep up. This problem cannot be solved by building enough electronic registers to store the program. That would be too expensive and make the machine too large. The solution is to use an electronic form of read-only memory, the resistor matrix circuit. This is a matrix of horizontal and vertical wires. A bit is stored at each intersection by connecting or not connecting a resistor between the wires at the intersection. This read-only circuit can be made mechanically variable by inserting switches to connect or disconnect the resistors. Moreover, these mechanical switches can be set automatically from punched paper tape. Hence, the program could be stored into the machine automatically from punched paper tape and then executed at electronic speeds. The general-purpose computer of the third stage of my story is a fast electronic version of the first two stages and has their simple modern architecture: an electronic central processor, an electronic read-write store for numerical data, and a program read electronically from read-only resistor matrix store. But now there is a mismatch. The elegant and fast electronics does not fit well with the electromechanical program entry equipment, which belongs to an earlier technology and has too many moving parts. An inventive engineer would want to improve on it. All the computers of our first three stages have the same hardware and software architecture, differing only in the technology for implementing it: mechanical, electromechanical, electronic. They are all general-purpose computers, capable of solving a wide variety of numerical problems under the direction of suitable programs. They are not stored program computers because they take their instructions from read-only memories. To get to the fourth and last stage, that of the stored program computer, we must have a new form of electronic read-write memory, one much cheaper than electronic registers, so it can be built sufficiently capacious to store the program as well as the data. The hardware and software of the earlier stages must then be redesigned to take advantage of the new opportunities. The program, now in read-write memory, can be processed arithmetically. It can even be processed by the same arithmetic unit which formerly processed only data. This completes my fictional story of how the stored program computer might have been born, how it would have been born if history were a good optimizer, if good ideas and the technology to achieve them appeared synchronously, if the creative designer were always a practical man and had adequate resources, and if novel ideas were always remembered and communicated to whosoever could use them. The actual history is very different. Each of my fictional stages occurred at least in some form and in some degree, but the causal connections and temporal sequence of my story generally did not occur. The actual derivation of the stored program computer is shown on the blackboard. The first stored program computers to be planned were the Moore School EDVAC, based on the sequential access mercury delay line, and the Institute for Advanced Study Computer, IAS, based on a random access electrostatic store. These came most directly from the ENIAC, which was the first general-purpose electronic computer. Somehow I have the differential analyzer. Go back one, yeah. There it is. Is that the best we can see? Okay. ENIAC stood for Electronic Numerical Integrator and Computer. The ENIAC was very different from the idealized computer of my stage 3, as you shall soon see, and it did not arise out of the general-purpose electromagnetic computer of stage 2. Indeed, the first such computers preceded ENIAC by only 2 or 3 years. The ENIAC was developed at the Moore School of Electrical Engineering of the University of Pennsylvania during World War II, mostly between 1943 and 1946. John Mauchly and Press Eckert were its main developers, but others made important contributions as well. I like to feel that I'm included in the latter group. The chief antecedents of the ENIAC were 2 machines radically different from it: Vannevar Bush's differential analyzer and John Atanasoff's electronic computer. The differential analyzer was the source of the ENIAC's architecture. The ENIAC's electronics started from Atanasoff's electronics, but went far beyond it in computing power, speed, and versatility. These derivations are traced in detail and documented in an article by my wife Alice and myself, which will appear next month in the Annals of the History of Computing, along with criticisms by others and our replies to them. The differential analyzer was a mechanical analog computer for solving differential and integral equations. This is the Moore School differential analyzer. Its main computing unit was the integrator. There are 14 of them on the right. It also used differential gears for adding and subtracting, and fixed ratio gears for multiplying and dividing by constants and for reversing signs. The tables on the left are for graphic inputs and outputs. The large bay of shafts and gears running down the middle was a flexible interconnection switch for transmitting numbers in the form of shaft rotations between units. The machine had to be set up for each system of integral equations. That is, the computing and input-output units of the machine had to be interconnected in a pattern appropriate to those equations. This is a schematic showing how to set up the machine for a particular second-order differential equation. The integrators are at the top. The motor driving the independent variable x is at the upper left, and there are two adders on the right. The interconnecting lines represent rotating shafts. Please note the architecture of the differential analyzer and how this architecture related to the mode of problem entry. The machine consisted of a number of computing and input-output units, all adjacent to a flexible interconnecting switch. This architecture became the architecture of the ENIAC, for that machine also consisted of many computing and input-output units, all adjacent to a flexible trunk system with many channels, a vast plugboard. This is a layout of the ENIAC. You can see the units around the U, and in front of the units is a strip showing the channel carrying the electrical signals. This is a part of the actual machine, and along the middle you can see switches where instructions were set. There are trays of wires running above, trays of wires running below, and many plugged cables going between these trays and the panels where the switches are set. When the ENIAC was computing, electrical pulses flowed in parallel between the units along paths established by setting up this vast plugboard. Here is part of a setup diagram I had drawn up early in 1944 to check our planned design. These represent the different units, such as accumulators, and the settings of switches to enter instructions on each of the units. The lines above represent wires carrying numbers, the lines below wires carrying program signals, and the interconnections up to the panels represent the sequencing of the instructions and the switch setting of the numerical communication switch. The units of the ENIAC, like those of the differential analyzer, operated in parallel, executing many instructions at the same time. Though the architecture of the ENIAC was similar to that of the differential analyzer, it differed in an important respect basic to the theme of this talk. The ENIAC was programmed, the analyzer was not. To explain how this difference came about, I first need to explain briefly how an integrator worked. The horizontal disk rotates according to the independent variable x. The vertical disk rides on the horizontal disk and rotates with it. How far it rotates when the horizontal disk rotates delta x depends on the distance to the center of the horizontal disk. This distance is controlled by y, the function to be integrated. The output of the vertical disk is thus the integral of y dx. This output must drive shafts, gears, and other units. It cannot do this directly without slipping badly, so a torque amplifier is inserted to amplify the rotational output. This shows actual units with the integrators. Here's an integrator, there's its torque amplifier, another integrator there, and there's its torque amplifier. You use a torque amplifier every day if your car has power steering. The differences as well as the similarities between the ENIAC and the analyzer are best presented in terms of a simple problem, the calculation of sines and cosines. Here are the equations, differential equations, integral equations, difference equation to produce the sine and the cosine. The analyzer will solve the integral equations, the ENIAC the corresponding difference equations. Here is the analyzer setup. Time supplied by rotations from outside is the independent variable there and there. The remainder of the setup is a feedback. The output of the right integrator, the cosine, becomes the input of the left, whose output, the sine, after negation, becomes the input to the right integrator. Now keep that feedback pattern in mind and look at the upper part of this diagram, which is how the ENIAC was connected up, two accumulators of it, to solve those same equations in different form. This is the upper part, the numerical part, in which a number is sent from there and received there, and then a number from here is sent and received over there. Now, digital integration involves multiplication by a constant delta t and accumulating the products. But if we let delta t be a power of 10, multiplication can then be accomplished by shifting wires, analogously to using a fixed ratio gear in the differential analyzer. These are the wire shifters, delta t and delta t. Thus, the feedback cycle at the top of this diagram is very similar to that of the previous slide. The right accumulator adds into the left through a shifter delta t, then the left accumulator subtracts into the right through another shifter delta t. This is iterated as long as desired. So much for the similarities between the differential analyzer setup of this problem and that of the ENIAC. But the ENIAC setup differs from that of the analyzer in having a program set up below. This difference derives from a more basic difference. The analyzer was an analog or continuous computer. The ENIAC was a digital computer. An analog integrator must receive and transmit at the same time, while a digital accumulator cannot receive and transmit at the same time. Consequently, we can feed an integrator back on itself to generate an exponential, but if we connect one of these accumulators to add or subtract back into itself, we get nonsense. Hence, the operations of these accumulators must be controlled, that is, programmed. This is done by the program set up below. And these are two program controls on that accumulator. These are two program controls on that accumulator. These are the wires over which pulses go to operate those program controls. An accumulator had its own program controls, each with a hand-operated switches specifying the functions of add, subtract, clear, and receive. A program control was turned on by a pulse, and when it finished, it turned itself off and emitted a pulse which could stimulate the program controls which were to be operated next. These local program controls were sequenced by plugging cables between them in the manner you saw in that earlier ENIAC slide and in the manner illustrated here. A program pulse at start caused the left accumulator to receive and simultaneously the right accumulator to transmit additively. When these program controls were done, each stimulated its neighbor, there and there, so that the left accumulator now transmitted subtractively and the right accumulator received what was transmitted. The numbers traveling along those upper connections. This slide shows how John Mauchly tested 2 prototype ENIAC accumulators in the summer of 1944. They were set up in this manner and calculated sines and cosines for months on end. This test proved that the ENIAC would really work. The program depicted here feeds back on itself. It eats its own tail, to use Babbage's apt way of describing hardware feedback in calculation. And so the machine could calculate indefinitely until a plug was pulled, that most ultimate of commands. We want the feedback in the numerical setup, but it must be controlled by the program setup. For this, the ENIAC had a higher stratum of programming based on the master programmer. And you can't see it very well. There are rows on rows of switches. I think maybe the next slide will show them better. Non-cyclic subroutines were set up on the local program controls of the units and sequenced by plugging in cables. They were then combined into a single program at this master programmer by plugging the routines into the plugs below and setting the switches above. The master programmer executed each subroutine in turn, either for some number of times as had been entered on these switches, or until a number in the calculation changed sign. Thus, the ENIAC had a special unit for the programming functions of counting iterations and of branching. Recall now my hypothetical history of the development of general-purpose computers through a succession of stages: first mechanical, second electromechanical, and third electronic. Let us compare the ENIAC with the fast electronic computer of the third stage, both intrinsically and in its origin. Recall that this hypothetical electronic computer of my third stage had a simple architecture: a central processor, a unified store composed of electronic registers, and a program set up automatically from punched paper tape, but read electronically. The ENIAC was also electronic and fast, but the similarities stop here. The architecture of the ENIAC was distributed, not centralized. Storage, arithmetic, and control were spread throughout the machine. Consider the 2 accumulators a few slides back that computed sines and cosines. They solved the problem autonomously, and yet they constituted only a small part of the whole machine. More important, ENIAC's method of problem entry was slow and clumsy, and hence badly out of balance with its fast electronics. It took 2 days to set up the machine to calculate trajectories of a shell fired from a cannon. But then the ENIAC could calculate the path of a shell that took 30 seconds to reach its target in just 20 seconds, faster than the shell could fly. Despite this, or perhaps because of it, the ENIAC gave rise to the modern stored program computer, with its elegant method of entering and executing programs and its simple architecture. Let us see how this came about. Eckert and Mauchly were well aware of the limitations of the ENIAC, though they were the chief designers of the machine. They were especially aware of the manual method of programming and its deficiencies. But they were also aware of the very limited data store, only 20 numbers of 10 decimal digits each. They sought something better. The first advance was the magnetic drum concept. Atanasoff had used 2 drums. One is up there in the Digital Museum. In 1942, Perry Crawford at MIT had suggested storing information on magnetic disks. Not as we use disks now, but having many disks on a shaft which rotated and magnetizing the edge of each disk. Press Eckert conceived of using a magnetic drum to store both data and program. This was in early 1944, and there's the drum there, and the relation to the, let's see, to Crawford over there. This was a good idea, much used later on, but it was still partly mechanical. It would be better to have a large electronic store with no moving parts. The next advance was the circulating mercury delay line. This was conceived by Eckert and Markley in the spring of 1944. Let me explain the principle first, and then its antecedents that are indicated over there on the board. Here is a tube of mercury with a crystal of the sort you have in your digital watch at each end. Electrical signals would come from these circuits. A signal would trigger the crystal, which would vibrate and put a pulse into the mercury, an acoustic wave which would travel down the mercury tube. Or at any given position, the crystal would not be stimulated and no pulse would go down. So there would be a sequence of pulses that would travel down the tube. When a pulse got at the other end, it would stimulate the output crystal, and an electric signal would now go back in. This used the principle of rejuvenation because the pulse at the end would not be nearly as sharp or well-timed as the pulse at the input, so there would be timing pulses from a central clock that would be used to reshape and retime the pulses. Information could be removed through an output of the circuit. New information could be put in to replace information already there. Atanasoff had used the idea of rejuvenation. He spoke of jogging the memory. The mercury delay line itself, with only one crystal at an end and a reflector of adjustable position at the other end, was invented by William Shockley of Bell Labs, one of the inventors of the transistor later on. He invented it for the purpose of radar timing. A radar would send out a pulse. Suppose the airplane that reflected that pulse was 100 miles out. Then after an elapsed time of about a millisecond, the radar pulse would come down. By sending a pulse down the mercury line and reflecting it back and adjusting the position of the reflector, one could have the mercury line pulse come down, come back in about a millisecond, and by appropriate calibration, determine how far the plane was out. The MIT asked the Moore School of Electrical Engineering to build a delay line of this reflecting variety for radar, and the Moore School asked Price Eckert to build this line. He did that in 1943. A little before, he worked on the ENIAC, and then he and Markley, in the spring of 1944, conceived of taking that mercury delay line and modifying it in the cyclic fashion so that it would become a computer store. This shows some actual delay lines, and Maurice Wilkes, who you can see better in person right here, they're tubes of mercury about so long, and the way they intended to be operated at the Moore School, a tube would have about a millisecond delay, and the pulses with microsecond spacing, so there would be about 1,000 pulses in each line. Gwen Bell gave me recently a delay line of approximately this capacity, operating on different principles and much more recent, the magnetostrictive delay line. It consists, and you can see this over in the museum in large form, of a wire which is circled around. Now, the mercury circulating delay line constituted an order of magnitude advance in electronic read-write stores. In the ENIAC, we could store only about 1 bit per vacuum tube, and this accounted for a lot of the ENIAC's 18,000 vacuum tubes. In one of these mercury lines, we hoped at the time to be able to store 1,000 bits with 10 vacuum tubes, plus the mercury line itself. This would be 2 orders of magnitude advance in electronic storage. And this would be the basis for a revolutionary new computer. However, at the time of its conception, everyone, Eckert, Markley, and the rest of us, was working very hard on the ENIAC, and so not much was done towards a new machine. In the meantime, von Neumann enters the picture. Hermann Goldstein was the military liaison between the Moore School and the ENIAC and Aberdeen Proving Ground, which was funding the ENIAC. And Hermann met von Neumann at Aberdeen on the railroad platform one time and introduced himself. Interestingly enough, von Neumann had earlier asked the government for information on computers of all varieties, and while he'd been told of most activities, he had not been told of the ENIAC. So Hermann told him about the ENIAC. Von Neumann was much interested and became a consultant to the Moore School. It was later decided to build a new computer based on a mercury delay line store. This was to be called the EDVAC, the Electronic Discrete Variable Automatic Computer. And in March 1945, von Neumann came to the Moore School for 2 days to discuss the nature of this machine with Eckert, Markley, Goldstein, and myself. Let me summarize the outcome of those meetings. It was agreed that there would be a mercury line store as big as possible. There would be a single serial adder and complementer, which would be used repeatedly for multiplication, division, and square rooting. Most of the 2 days were spent on hardware design. The design of switches for reading and writing in the mercury memory, to choose a line, to choose a word within a line, to route the chosen word, which could be either a number or an instruction, to the arithmetic unit if it was a number, to control circuits if it was an instruction. And considerable attention was given to the design of vacuum tube binary adders. These would operate on a sequential basis like those of Atanasoff, but at much higher speed. And that was a different mode of operation than the adders of the ENIAC that were based on counters. It was planned that there would be orders or instructions for transferring numbers between the memory and the arithmetic circuits, and for specifying arithmetic operations. But beyond this, almost nothing was said about the order code or how the control would operate after an order was transferred to it from the memory. Let me note for historical reference that in the case of the ENIAC, the hardware for storage and arithmetic was designed first. Then the local programming circuits, which you saw illustrated in the 2 accumulators, were designed next. And the master programmer, which handled the subroutine set up on the local programming circuits, was designed last. I should note, too, that at this time, we all knew of punched paper tape programs that were used in electromagnetic relay machines. At the end of these 2 days of meetings, von Neumann offered to work on the new machine. This was an offer accepted with alacrity. He went off to Los Alamos to consult on the atomic bomb, which he did regularly. In 2 months, he sent back a draft report, what became the famous von Neumann report on the EDVAC, that was distributed in June 1945. Before describing von Neumann's 1945 report, let me tell you a story of what happened at one of our meetings. In discussing serial binary adders, John Mauchly described several vacuum tube circuits, each containing about 10 tubes for an adder. Von Neumann said that he could design a satisfactory binary adder with 5 tubes. We acted very surprised, and he went to the board, and he drew a circuit, but not a circuit in terms of vacuum tubes, a circuit in terms of logical design using switching elements and delays. Switching elements for and or not, delays that would delay pulses for 1 pulse time, planned at that time to be 1 microsecond. He did have a diagram with 5 of his tubes, but when we thought of replacing his logical symbols with vacuum tubes, we could see that it wouldn't work. As we said, well, this tube can't drive that other tube fast enough, so you'll have to put in an additional tube as an amplifier. And when you do that, that will reverse the polarity and produce a negation, and so another tube must be put in to negate that negation. And so it went. And finally, he was convinced that it would take 10 vacuum tubes. But he was nonplussed. He stepped back, looked at the diagrams, said, "You're right, it does take 10 tubes. 5 tubes for logic and 5 more tubes for electronics." By using those logical symbols, von Neumann postponed matters of electronic circuit design and was able to work out much of the logical design and architecture of the EDVAC and most of the code or machine language for the internal operations in this report. I won't describe von Neumann's design very much in detail for a reason that will become apparent in a moment. The general architecture was that you're familiar with: a memory, an arithmetic unit. It was to have 3 short lines, or lines 1 word long each, as registers, and a central control. In the meetings, it had been suggested that the base conversion from binary to decimal and back again would be done at input and output. Von Neumann introduced explicit instructions for decimal binary and binary decimal conversion. In the meetings, we had considered whether there should be 1 switch from the memory going both to the arithmetic unit and the central control, or whether there should be 2 switches so that orders and numbers could be removed simultaneously in order to accelerate the execution. Von Neumann chose 1 switch, but then he used the first bit of a word, the least significant bit for numbers, the first bit to come down the line. He used the first bit of a word to route orders directly into the control and numbers directly into the arithmetic unit. So an order coming out of a delay line could operate on the number coming out immediately after that from the same delay line. In designing his code, he faced explicitly the problem of how to minimize waiting time for a sequential access memory. Now, this complicated the code, And to avoid describing this complication, I'll pass on to the next stage of the development, the random access memory. Though von Neumann's EDVAC design in the 1945 report was for a machine based on the mercury store, in that same report he proposed using a cathode ray tube, TV sort of tube, as a random access store, storing bits of information on the face of the tube in the form of charges or the absence of charges. Jan Reichmann of RCA said that he could build a special cathode ray tube that would do just that. And this tube, before it was built, and later too, of course, was called a selectron. On this basis, von Neumann, Goldstein, and I, in 1946, produced our design of what I've called the Institute for Advanced Study machine. I'll now show some slides leading up to this machine and conclude by explaining how it was programmed. This is a selectron. You can see one of four faces. You can barely see some windows. Behind these windows there is a matrix of wires, vertical and horizontal. By controlling the potentials on those wires, one can open or shut electrically one of these windows, keep most of the windows shut, open one, and allow the beam of electrons to flow through. The electrons can be deposited on the corresponding spot for a 1, not deposited for a 0. If the beam then flows through at a later time, there will appear a voltage which can be detected and the information read out. This memory would be alternately used and rejuvenated because, of course, the charges on these neighboring spots would be close to one another and they would gradually drift off, so the information would be lost, just as in Atanasoff's electrostatic store, the condensers could gradually discharge. So one would use the tube in this moment for writing or reading a bit, and then the alternate moments systematically scan all the information in the tube and build up charges to the proper level. Now this tube was not developed fast enough to be used in the Institute of Advanced Storage Computer. The actual tube that was used was invented by F.C. Williams in England, called the Williams tube, and this was an ordinary cathode ray tube with a screen of wire on the front for reading the signal in the tube. This operated on the same general principle, but it didn't require a special tube. It didn't require all that internal structure. This slide shows a Williams tube as used in the Institute for Advanced Study computer. Tube along here, you can barely see the screen of wire used for reading the information, and those cylinders behind are electrically insulating cylinders in which the tubes are placed. Here is a picture of the whole machine with von Neumann on the left. Here is the circuitry. You'll see in the moment there's another side. Here are 40 Williams tubes, 20 on this side, 20 on the other side, so that the words of this machine were 40 bits long, and each word was able to store one instruction with a single address. This shows the machine from the end, the side that you just saw, and then the other side. These are various meters for measuring the voltage going on. These 40 bits would be stored in parallel. That is, for each word, one bit of the word would be in one of those tubes, so that each tube would store a single bit for all of the words of this memory. The instructions were to be executed in order, starting from the 0 word. Since there are 2 instructions, left and right, the left instruction would be executed, then the right. Then the control would move automatically to the first word, execute the left and the right, to the second word, etc., except, of course, for branching. This is the architecture of the machine. Here is the store. There is a register called the Selectron register. And in the code that I'm going to present in the next slide, S of X will mean Selectron position X. And the plan of the machine was to have 4,096. So this would range from 0 to 4,095. Here is the accumulator. There's a register. This is the equipment for the arithmetic unit. Here is the control. Words that were control words taken out would be moved into the control. It would send signals and addresses over to the store and the rest of the machine. In the code that I'm going to show you next, you'll see the symbols S of X, meaning the word in the Selectron memory at position X, A for accumulator, R for register, and C for control. So I want next to show you the IS code and then illustrate very briefly how it worked. Here are the instructions in full form. We can ignore those in abbreviated form. These first 8 instructions are for moving numbers from the Selectron into the accumulator, performing additions and subtractions. S of X into the accumulator with the options clear or hold, add or subtract, and send in either the modulus or absolute value or not. And that accounts for 8 instructions. One could also transfer numbers from the memory into the register, from the register into the arithmetic unit, take a number in the memory, multiply it by a number in the register, and put the answer in the arithmetic unit. One could take a number that was in the arithmetic unit, divide it by the number of position X of the memory, place the answer in the register. These were the arithmetic operations. The instructions, as I said, were taken in sequence, except that when you want to jump, you have to go to another point in the memory. Here is the unconditional transfer from wherever the control is to the parent instructions in position X. And there are 2 varieties, unprimed and primed. The unprimed taking you to the left instruction, the primed to the right instruction. Here's the same pair for conditional jump, jumping when the sign of the number in the arithmetic unit was non-negative. Going back into the store, one could go from the accumulator totally, that is, take the number in the accumulator and put it in the Selectron memory. But there are also 2 other transfers, one left and one right, that took a number from the accumulator. But this would not be a full number of 40 bits. This would be 12 of those 40 bits. 12 bits for the address, since there are 4,096 bins in the Selectron store. This operation would take the leftmost 12 bits of the accumulator and replace the address part of the left instruction in bin X of the memory. And this operation would take the leftmost 12 bits in the accumulator and replace the address part of the right instruction in that position of the memory. Here's a left shift, and there's a right shift. With these instructions in mind, at least the general idea of them, let us show how a very simple problem would be calculated. Let V sub I be the sum of the product of xj, yj from j equal 1 to I. We want to calculate V1 ranging from 1 to 100, which will keep track of the calculation and which will be used to compose addresses so we can, in parallel, scan this part of the memory and this part of the memory, picking up these pairs xj, yj together and multiplying them and adding them into the VI. A 1 for the increment on the I and 100 on the bound for the I. The program I'll represent by this flow chart, which will have 3 parts. You start and compute. You then specify the addresses for this operation of scanning the memory for the x vector and the y vector. Then test and branch and loop until the problem is finished. Here is the computation part. That is, the first instruction is to take xi on its first operation. I will be 1, so it will take x1, which is in position 101, and transfer it into the register. The next operation will pick up the yi multiplied by what's in the register, put it in the accumulator. Then we'll add the v that's been built up so far to produce the new v, add, that is, take the number from the selectron, put it in the accumulator, holding what's already there, and do this additively, and then store that vi. And you notice that initially this instruction will be S101 into R, and this instruction S201 into R, and those addresses will be modified by the next part of the flow chart, which first takes out the index, increments it, and stores it, so I will be increased by 1, but then it forms the address 100 plus I by adding 100 to that index, and using the partial substitution substitutes that to pick up the x, and adding another 100 to get the address 200 plus I to pick up the y, substitutes that partially in the instructions that you saw in the first part of the program. And then finally, we form 100 minus I minus 1 in A and branch on this. This is the flow chart again, so that you can see these operations of compute, specify, which means to calculate the index and substitute addresses in the instructions of the compute box, and then the branch. Now let me distinguish programs that are in read-write memory from programs that are in read-only memory. The program that was read from the selectron memory, we can ask of it, was any of it written in or modified? And the answer is that yes, that first part, the compute part, had addresses that were used to pick out xi and yi, and they were substituted in this read-write memory. Now compare what the earlier ENIAC program for the sine-cosine would look like. In that case, we used only 2 accumulators, 2 registers for memory. The accumulators were also doing the adding and subtracting. We didn't have to scan the memory, so an instruction code for that, which would be roughly the length of this 2, would not need this specify part of the program to change the addresses of the earlier part of the program, and therefore it could be stored in read-only memory. And of course the ENIAC plugboard memory, where you plugged in cables and turned switches, was read-only memory, and a memory punched on paper tape was read-only memory. So with this we can distinguish 2 kinds of programs and program languages. The program for the vector problem has variable addresses, and that program needs to be stored in read-write memory. The program for sine-cosine calculation has only constant addresses. It can be stored in a ROM. Equivalently, in this code, the program for sine and cosine calculation does not use the partial substitution operation of this IAS code. So we speak about variable address programs and constant address programs. The first requiring read-write store, for the second, a read-only memory is adequate. Now, what is the relevance of this to the transition from ENIAC to EDVAC? At the time of our March meetings with von Neumann, the only program languages we knew of were constant address programs, the ENIAC programs, punch paper tape programs, stored in read-only memory. Note that given the small size of the read-write memories of these machines, such as the ENIAC, for storing numbers, these read-only programs were adequate. There was no need to scan the memory, as in this vector problem, because the memory wasn't large enough to hold all those numbers. In his 1945 EDVAC report, von Neumann produced a new type of program language, the variable address program language, with which we are all familiar now. This was his unique contribution. Let me very briefly summarize the origin of the stored program computer and make some evaluations. Let me emphasize that my talk has been limited to the initial conception and logical design phase, what happened up to 1946. The final design and construction of the stored program computer came later, and many not mentioned here made contributions. There were two types of the stored program computer. First the EDVAC, then the IAS. They both had the simple internal architecture of store, arithmetic unit, and control. They both executed one instruction at a time. The EDVAC had a sequential access store and handled words bit serial. The IAS had a random access store and handled words bit parallel. These designs came most directly from the ENIAC, which was the first general-purpose electronic computer. Now, the ENIAC did not come from any earlier general-purpose computer. Rather, it came from two computers, neither programmable. Atanasoff's electronic computer, though the ENIAC exceeded it in speed, power, and generality, and the mechanical differential analyzer, from which the ENIAC got its distributed architecture and its principle of executing many instructions in parallel. The next stage was the development of the stored program computer because of the inadequacies of the ENIAC, especially its mechanical plugboard method of programming. Who created the stored program computer? Many contributed to the background. Eckert, Mauchly, and von Neumann were the main creators. Hermann Goldstein and I played a role in the later version based on the random access store. Finally, let me return to the very beginning of my talk, where I said that the stored program computer differed from its predecessors in two basic respects. Hardware, a new kind of read-write memory sufficiently capacious to store the program as well as the data. Eckert and Mauchly saw the need for this memory, and they invented the first one, the Mercury delay line store. Second, software. The stored program computer executes a new kind of program language, one that takes advantage of the new way of storing problems, code. Von Neumann was primarily responsible for this contribution. I thank you.
If there are questions, why don't you come up? You're a professor. You can do it.
Yes, I can. Let me get a little more water. If I may. Because of the light, I'm not sure I can see people. Speak out.
I'd like to say there's a selectron tube in the memory case that you can all go look at, and there's a Williams tube sitting upstairs on the timeline.
And there's part of the ENIAC sitting at the top of the stairs. Actually, one of the 40 panels, a panel from one of the 3 function table units, which were read-only memories for storing functions, especially since the ENIAC was funded by the Department of Defense for computing firing tables. The function which gives the resistance of the air to a shell as a function of velocity was stored in a function table read-only memory. Yes, back there. Well, I think I'll refer that question to Maurice, because you see, I left the Moore School after the dedication of the ENIAC in February of '46, and I went to the Institute and worked on the IAS design, so I was no longer involved in mercury delay lines. I think Maurice told me once that before he had his electronic working properly, he could create pulses down the line by banging a door or something. Is that true?
No, that is not quite the story.
It's a better story.
The mercury delay line was quite insensitive to mechanical vibration because, in our case, the carrier frequency was 13.5 megacycles, and banging it with your fingers doesn't produce much component in that band. So that was perfectly all right. But the story is that when we first set it up, we had a lot more gain than was necessary. We had no way of putting pulses in, but we found if we switched the light on in the room, a very convenient way of putting 2 pulses in.
All right. Yes. He's asking me to repeat the question, and that, is there another question? That was a question about how reliable the mercury line was. Yes.
I read some anecdotes about how bright it was.
Yes.
Any personal anecdote about it? You may perhaps be the science.
Well, thank you for the compliment. The question was how bright was von Neumann, and what anecdotes I could tell about him. Well, I did tell an anecdote, that story about 5 tubes for logic and 5 tubes for electronics. He was very quick to understand these matters, that though he was known as a mathematician, he had had some training as a chemical engineer, and though he didn't know a great deal of electronics when it came to specific tubes and their properties and so forth, which is one reason that he elected to use these logical symbols rather than the vacuum tube symbols we were using in his design, he understood it rapidly enough to settle the important issues. I guess the thing that impressed me most about him was that this EDVAC report, which was about, I remember, 100 type pages, something like that, was a single draft that had been written continuously, starting from the very beginning, leaving various options open, not only how big the memory could be, because we didn't know how big a memory would work, but various design choices that could not be made until you knew something later, but you couldn't do something later until those choices had been made. That is the general problem of whether you design from the bottom up or the top down, and of course you have to cycle around and do both. He solved that problem in his draft by leaving open various options, carrying them all in his mind, and working through the paper to the end of the paper. If I could write a first draft like that, I wouldn't have to write 10 drafts of what I write. Yes? Well, the way I view it is this, that indices perform different functions that I've tried to differentiate here. One was the matter of counting loops or iterating. The other is the matter of scanning memory. That in the case of the ENIAC, and I was responsible for the basic principles of the design of the master programmer, we had counters that would count iterations up to numbers set on the switches. That's what those switches were in the diagram. We didn't need the indices, as I explained, because we didn't have enough memory to scan. What was impressive to me in the von Neumann design of the ENIAC, of the EDVAC, was how that von Neumann had consolidated functions in the arithmetic unit which we had handled in many different ways in the ENIAC. As the function of counting loops is handled by having an index I and incrementing it and comparing with a bound. The function that we didn't have of scanning a region of memory handled by calculating the I, adding the starting point of the area of memory and substituting it in. But that same method could be used to pick an arbitrary function. So if we had a function of 100 values in bins 101 to 200, exactly the same method would be used to take an arbitrary argument x, convert it into I, and add the beginning of the memory area to look up f of I plus 100. As we could pick out x of I by looking up f of I plus 100, or s of I plus 100. Now the function table up there had its own switch for scanning its read-only memory of 100 function values. So the impressive thing was to consolidate these functions, which had before been separate. Then, as designs went on and equipment got smaller so that you could put more hardware in the sense of more circuits to do more things, then these various functions could be transferred back to special units such as index registers. But it is important to keep in mind that the original ENIAC had 18,000 vacuum tubes. The goal was not only to have a machine with no moving parts, that is none of this electromagnetic or hand setting of instructions, but also a small machine to get from that 18,000 tubes down to something like 3,000 tubes, which is what we were counting on for the EDVAC and the IAS. And the implication of that, that von Neumann saw was, well, you could minimize the number of tubes by having a simple arithmetic unit with an accumulator and a register that could perform all of these functions. Over there? Or did you want to say something, Maurice? Somebody over there wanted to ask a question. I don't know how long you want to go on. I'm all right. Actually, when Herman, the question was, did Einstein express any opinions about computers while I was at the Institute? And the answer is I didn't know him that well. Actually, when Herman and I first went there, we had an office next to Kurt Gödel's, and Einstein came in quite often to meet Gödel and go for a walk, and he was friendly and so forth. What he said to von Neumann I couldn't say, except for the following, that the Institute of Advanced Study at that time, and still true, was not an engineering research institute, of course, but a highly theoretical institute in its orientation. And so the idea of a computer didn't fit with what they normally did. However, von Neumann himself not only was a full professor at the Institute, but they had sufficiently great respect for him that if Johnny wanted a computer, the Institute would have a computer. Yes?
Did any of these machines ever were used to process character data?
The objective of the EDVAC and IAS was primarily an objective of scientific computation. One can always code alphabetic information, of course, as has been recognized at least since Leibniz. And one of the problems that was considered was the problem of ordering files. And actually von Neumann, after he gave this design of the EDVAC, considered the problem of ordering files by a process of repeated merging of sequences. So this was somewhat like a data problem. No special means were taken in these computers to make it particularly easy to handle data. Of course, Press Eckert and John Mauchly were interested in the commercial applications of this. So after they built their BINAC, which was a scientifically oriented machine, they went ahead and worked on the UNIVAC, which has many features in its architecture to make it easy to handle alphabetic information. Yes?
When these ideas were being developed, was programming a specialized thing, or could most anybody attack it using the program?
Well, in the case of the ENIAC, the programming didn't really exist until the machine was there. I showed you a schematic diagram for interconnecting both the numerical circuits and the programming circuits of the ENIAC, which is drawn up in 44. People began to program the ENIAC in late 45. It solved its first problem in December of 1945, which happened to be a Los Alamos problem, still classified, though it's known that it was on the H-bomb. And then various young women who had been computers in the human sense of operating desk machines, calculating trajectories and the like at the Moore School, went to work and learned how to program this. As soon as we had time to work on the programming aspects of the new machines that we did, though of course the hardware had to have a certain priority. We started some reports on programming. Then I left the Institute. My wife and I went back to Michigan, but these were done by Goldstein and von Neumann, introducing flow diagrams and so forth. I used to commute from Swarthmore to Princeton, and on the train I can remember working out programs to try to establish a library of routines so that one would have routines for various aspects of the computing process. Yes? Well, initially, you really did it in machine language, and you would transfer it into the binary or octal or whatever form. As soon as possible, of course, people made converters to simplify this. I actually didn't become a computer user, but went on and did other things in the theory of automata, so I'm not really very qualified to answer that question. Well, we used a terminal, but not an intelligent terminal. The question was how we accessed the machine, and there was a typewriter or a punched paper tape. Maurice, were you going to say something about that? Yes.
I'm not quite sure how to put this, but I would like to be sure that I understand what you've been telling us tonight about von Neumann's role. No one disputes that von Neumann had long discussions at the Moore School with yourself and your more senior colleagues. And no one disputes that von Neumann went away and wrote a report. What is not clear is to what extent what went into the report was his own contribution, and to what what extent it was suggested to his very quick mind by the discussions that took place. Now, as I take it, you are giving us testimony. There is, well, as far as I know, there are no documents that will ever settle this question. You are giving us your testimony as a witness, are you, on what you recollect happened?
That's right, and that's why I spent some little time on the state of our thinking at the time of these meetings. However, it isn't true that there are no documents, because I did take notes at those meetings, and they were in the file. All of these documents were classified, and so I was not able to carry any of the notes away with me, and indeed I'd forgotten that I had taken those particular notes, though I wrote many of the reports at the Moore School. But during the ENIAC trial, the trial concerning the validity of the ENIAC patent, those notes were uncovered. So, and these notes generally support or turn it around. What I said in this talk is based not only on my memory, but what items were listed in those notes. Yes?
Did Neumann have any knowledge of developments in England at that time, especially
That's one of the debate. Question was, what did von Neumann know about the Colossus, which was the first electronic computer to operate. It operated, as I remember, in 1942, and then there were other models of them. A machine for making analysis of codes in order to break the codes, a machine which is still classified as to its circuitry, though it's known that the coded information was put on a paper tape, read into the machine. There was some kind of a plug board which could be used at least for changing the switching functions, the functions that one would make of the input data for the purpose of analysis. I do not believe, well, there's no evidence, no good evidence that I know of that von Neumann knew about the Colossus or had what someone suggests as a secret meeting with Turing over these matters. There could, of course, occurred without any record now available. Yes? That's right. You should ask them. Question was, would Eckert and Goldstein agree with this interpretation? Any other questions? Not, thank you very much.